Hi all. In this video, we are going to cover the module 6 of Structural Analysis 3 by APJ Abdul Kalam Technological University through a question paper. Okay. Today I'm going to look at the question of December 2018. There are two questions from this module. They are explain the logarithmic decrement and derive the equation for logarithmic decrement. Second one is derive the response of the free vibration system with damped case and calculate the free vibration response of SDOF system at time t is equal to 0.2 second for the following data. Natural frequency omega is given, damping coefficient zeta is given, and initial velocity, initial displacement. Okay, so let us see the first question first. Explain the logarithmic decrement. Derive the equation for logarithmic decrement. So, logarithmic decrement is a practical method for finding out the damping coefficient, and it is usually done by initiating a free vibration to a system, and we will obtain the record of oscillatory motion, and from this oscillatory motion's record we will measure the rate of decay of the amplitude of the motion, and this decay is expressed by logarithmic decrement. So we can define the logarithmic decrement as the natural logarithm of ratio of any two successive peak amplitudes x1 and x2 in free vibration. So this is the figure. See, you can see a damped vibration here. The amplitude is decreasing, and this is the peak vibration of first vibration x1, and the next peak vibration is x2. So we are going to find out the decrement or decrease in the amplitude, and it is expressed in delta or logarithmic decrement is equal to natural logarithm of x1 by x2. So let us see how to derive the value of this natural and logarithmic decrement. For that, let us consider a damped vibration represented graphically like this. And we know for a damped vibration, equation for x is equal to e raised to minus nt c1 cos root of p square minus n square into t plus c2 sine root of p square minus n square into t. This portion we have discussed in the last video. The equation for damped free vibration is this. So we can say at time t1, that is for the time period t1, the vibration is not starting from this point, it is starting from some other point. Okay, so the time taken to cover to reach x1 is t1, and if time taken to reach x2 is t2, and the time period for this vibration, we can calculate the time period. Time period is the time required to complete one full cycle, or we can write time required to complete from this point to this point to this point. Okay, so time required to reach the vibration from this point to this point is known as capital T or time period. So for x1, we can write the equation in terms of t1, that is x1 is equal to e raised to minus n t1 c1 cos root p square minus n square into t1 plus c2 sine root p square minus n square into t1. Then x2 is equal to, we can write e raised to minus n t2 plus c1 cos root p square minus n square into t2 plus c2 sine root of p square minus n square into t2. So this is the equation for x2. This is the equation for x1. Now we can see from this figure t2 is equal to t1 plus time period. T2 is equal to t1 plus t. Or we can write t2 for a damped free vibration. Time period is calculated by using equation t is equal to 2 pi by root of p square minus n square. This is the equation for calculation of time period in a damped free vibration. Okay, then our T2 can be written as t1 plus, instead of t we are substituting this equation, so t1 plus 2 pi by root of p square minus n square. Okay, so our equation for x2 will become, instead of t2 and substituting t1 plus 2 pi by root p square minus n square, so x2 is equal to e raised to minus n, t1 will become t1 plus t2 by root of p square minus n square, and c1 cos root p square minus n square into t2, instead of t2 I am substituting t1 plus 2 pi by root of p square minus n square. Similarly, plus c2 sine root of p square minus n square into t1 plus 2 pi by root of p square minus n square. Okay, so this equation we are substituting t2 in terms of t1 and capital T. Okay, now I'm just going to expand this equation, that is e raised to minus n into a plus b is e raised to minus n into e raised to minus na into e raised to minus nb, that we all know equation, that e raised to ax can be written as e raised to a into e raised to x. Right? Similarly, I can write e raised to minus n into t1 plus 2 pi by root p square minus n square can be written as e raised to minus n into t1 into e raised to minus n into 2 pi by root p square minus n square. And I'm just multiplying this p square minus n square into this. So p square minus n square into t1 plus root of p square minus n square into 2 pi by root p square minus n square. Similarly, I'm just multiplying this sine p square minus n square into this bracket. So this will become sine root p square minus n square t1 plus root of p square minus n square into 2 pi by root p square minus n square. Now look at this. Here in this term, you can see root p square minus n square into 2 pi by root p square minus n square. So these two terms will get cancelled each other. And here also these two terms will get cancelled each other. Then the equation become x is equal to e raised to minus nt into e raised to minus 2 n into 2 pi by root of p square minus n square into c1 cos root p square minus n square into t1 plus 2 pi, because these two terms get cancelled, and c2 sine root p square minus n square t1 plus 2 pi. And what is cos 2 pi plus theta? It is cos theta itself, right? So cos 2 pi plus theta or sine 2 pi plus theta is become cos theta and sine theta itself. So we can write, see, this is sine theta. So we can write this equation as e raised to minus nt1 into e raised to minus n 2 pi by root p square minus n square into c1 cos 2 pi plus theta become cos theta. So cos root p square minus n square t1 plus c2 sine root p square minus n square t1. So you must remember, since it was added with 2 pi, this term get cancelled because cos 2 pi plus theta is cos theta and sine 2 pi plus theta is sine theta. That is how we got this equation in this manner. Okay, so the x2's equation, I'm just taking this into here and I'm just rearranging these two terms. Then x2 will become x2 is equal to e raised to minus n 2 pi by root p square minus n square into e raised to minus n t1 c1 cos root p square minus n square t1 plus c2 sine root p square minus n square into t1. Then what is this term? This is the equation for x1, or I can write this as x2 is equal to e raised to minus n 2 pi by root p square minus n square into x1. Okay, so this term is equal to x1. So this is the equation for x1. So I'm just substituting this entire term is as x1. So we can write x2 is equal to e raised to minus n 2 pi by root p square minus n square into x1. Now, since it is minus e raised to minus x, e raised to minus x can be written as 1 by e raised to x. So e raised to minus n 2 pi by root p square minus n square can be written as 1 by e raised to, here it is 1 by e raised to n 2 pi by root p square minus n square is equal to x1 by x2. So I am taking this into right hand side and this into left hand side and this into right hand side. So this will become 1 by e raised to minus n 2 pi by root p square minus n square is equal to x1 by x2, and you know 1 by e raised to minus x is e raised to x, or this term will become e raised to x. E raised to n 2 pi by root of p square minus n square is equal to x1 by x2. So see, I'm just taking this term into left hand side and x2 into right hand side, then the equation becomes this. And since 1 by e raised to minus x will become e raised to x, or e raised to n into 2 pi by root p square minus n square is equal to x1 by x2. And what is e raised to x is equal to a? Then we can write x is equal to natural logarithm of a. So in this manner, we can rearrange this equation as n into 2 pi by root p square minus n square is equal to natural logarithm of x1 by x2. See, look at this equation. What is ln x1 by x2, which is known as logarithmic decrement. So we got the equation for logarithmic decrement, that is logarithmic decrement ln x1 by x2 is equal to 2 pi n by root of p square minus n square. And just dividing numerator and denominator of this term, numerator and denominator of this term with p. So 2 pi n by root p square minus n square. When I divide both terms with p, then it will become 2 pi into n by p by root of p. When p get inside the root, it will become p square. So p square by p square, which is 1 minus n square by p square. Now I am naming this n by p. N by p is known as critical damping ratio, or it is indicated by the term zeta. So n by p is zeta, which is critical damping ratio. I am substituting this n by p with zeta, then we can write the logarithmic decrement delta, or ln x1 by x2 is equal to 2 pi zeta by root of 1 minus zeta square, where zeta is the critical damping ratio. So this is the equation for logarithmic decrement, and this is how we derive it. The next question is, derive the response of free vibration system with damped case and calculate the free vibration response of single degree of freedom system at time is equal to 0.2 seconds, and full name of the data is given. Okay, so in this question, first we have to derive the response of the free vibration system with damped case. And for free damped vibration, we have the equation of motion as mx double dot plus cx dot plus kx is equal to 0. And this is a linear differential equation of second order, and solving this equation will give the solution for value of x is equal to a into e raised to lambda t. So we know, since x is equal to a into e raised to lambda t, x dot, which is dx by dt, is equal to dx by dt is equal to a lambda e raised to lambda t, and x double dot, which is equal to d square x by dt square is equal to lambda square a into e raised to lambda t. So now the equation of motion will become, when we substitute the x dot, x double dot and x in terms of a e raised to lambda t, the equation of motion will become m into lambda square a e raised to lambda t plus c into a lambda e raised to lambda t plus k a e raised to lambda t is equal to 0. Now solving this equation, when you take this equation, a into e raised to lambda t is a common term, so I am just deleting that term from all those terms. Then our equation becomes m lambda square plus c lambda plus k is equal to 0, which is a quadratic equation. And we know how to find out the solution root of a quadratic equation. Lambda is equal to minus b plus or minus root of b square minus 4ac by 2a. In similar way, here lambda is equal to minus c plus or minus root of c square minus 4ac. Here a is m and c is a. So 4mk divided by 2m. So we can write minus c by 2m plus or minus root of c by 2m whole square will become c square by 4m square minus 4mk by 4m square. When 2m get inside the root, it will become 4m square. Okay. So we can write minus c by 2m plus or minus root of c by 2m whole square minus k by m. And we know k by m is p square, and we are naming the c by m as n. So the equation becomes lambda is equal to minus n plus or minus root of n square minus p square. And so we can write there are two terms, lambda 1 and lambda 2. Lambda 1 is minus n plus root n square minus p square, and lambda 2 is minus n minus root n square minus p square. And according to the real values of n and p, there are three cases. First case is n greater than p, that is overdamped system. In this, when n is greater than p, we can say n greater than p, this will be a positive value. This is also will be a positive value, but root of n square minus p square will definitely be less than n. Since n square is root n square is n, so root of n square minus p square will be less than n. So both will have lambda 1 and lambda 2 value will be a negative value and a real value. Okay, so we can write x is equal to a1 e raised to lambda 1t plus a2 e raised to lambda 2t. So the solution does not contain any periodicity, hence it doesn't represent a vibratory motion. And the two terms in right hand side, that is a1 e raised to lambda t and a2 e raised to lambda t, they decay exponentially at two different rates. Even though the lambda 1 predominates for a short time, however it goes on decreasing in an exponential manner with the time. And the displacement finally vanishes at the time t is equal to infinity. Okay, so that is the overdamped case. Next case is n is equal to p. So look at our root lambda 1 and lambda 2. When n is equal to p, the values are minus n. That is, both are real and negative and equal. So our x value will become a1 e raised to lambda 1t plus a2 e raised to lambda 2t, where lambda 1 and lambda 2 are lambda. So we can write x is equal to a1 plus a2 e raised to lambda t. And the displacement of the mass reaches zero asymptotically with time for this case. And damping in this case is great enough, not great enough to set up an oscillatory motion. See, this will be the damping case. It will damping will stop asymptotically by the time t. Okay, and the value of when n is equal to p, we know when n is equal to c by 2m, and p is equal to k by m, root k by m. Here n is equal to p. When n is equal to p for critically damping case, so for this damping constant c is represented as CCR or CC by 2m, where CC indicates a critical damping constant or critical damping coefficient. So CC by CC is known as critical damping coefficient, or which is equal to, if we write n is equal to p, which is equal to cc by 2m, we know c by 2m is n and cc by 2m is equal to n or equal to p. So we can write c by 2m divided by cc by 2m can be written as n by p, which is equal to c by cc is equal to n by p, which is named as critical damping coefficient or damping factor. It is represented by the symbol zeta. Okay. Now moving to the next case, that is damped case or underdamped case. Underdamped case is also known as damped case, simply damped case. So here n is less than p. So when I substitute n less than p, then look at this root. Here when n is less than p, the root will become negative, right? So we can write minus p square minus n square. Minus 1 into p square minus n square, where root minus 1 is I, which is a complex value. So minus n plus I into root p square minus n square, lambda 2 will become minus n minus I into root of p square minus n square. So the roots are complex and they are x equal to a1 into e raised to minus n plus I root p square minus n square. A2 is equal to e raised to minus n minus I root p square minus n square into t. And as e raised to I x is equal to cos x plus I sin x, e raised to I into root e raised to minus n plus e raised to I into root p square minus n square t can be written as e raised to minus nt into cos root p square minus n square t plus I sin root p square minus n square t. This term represent e raised to I into p square minus n square into t. Okay. So e raised to I into root p square minus n square t can be written as cos root p square minus n square t plus I sin root p square minus n square t. And similarly, e raised to minus I root p square minus n square can be written as cos root p square minus n square t minus I sin root p square minus n square t. And when I rearrange, taking e raised to minus nt as common, it will become a1 plus a2 into cos root p square minus n square t plus I into a1 minus a2 sin root p square minus n square into t. Then substituting a1 plus a2 as c1 and I into a1 minus a2 as c2. So the equation become e raised to minus nt into c1 cos root p square minus n square t plus c2 sin root p square minus n square into t. So this is the general equation for damped free vibration. Now, in order to find out the values of C1 and C2, we are substituting the initial condition, that is, at time is equal to 0. At the 0th time, the displacement x is equal to initial displacement x0 and velocity will become initial velocity x dot 0. Substituting these into this equation, when I differentiate this one, you will get the x dot equation of x dot. And when I substitute, the values will become C1 is equal to x0 and C2 is equal to n x0 plus x dot 0 by root p square minus n square. And that differentiation part and other explanation is given in the previous video. If you want to see that, you can watch the previous video, module 6 part 1, previous year question paper solution. There I have explained it clearly. So I'm just writing down the values of C1 and C2 here. So C1 is x0 and C2 is nx0 plus x dot 0 by root of p square minus n square. So this is the equation for a damped free vibration by substituting the values of C1 and C2. Now you must know that natural angular frequency gamma omega is equal to root of p square minus n square and time period is 2 pi by omega or 2 pi by root p square minus n square. Usually we used to take these values for the problem. That's why I mentioned here. Now let us come back to our question. Our derivation part is over. It was asked to derive the response for damped case. I have explained all the three cases. Okay, so for the damped case, calculate the free vibration response. So we have, it is given x0, that is initial displacement is 5 centimeter, which is 0.5 meter, and natural frequency is 12 rad per second. X dot 0, initial velocity 10 centimeter per second, which is 0.1 meter per second. Time is 0.2 second, and damping coefficient, which is n by p, is 0.15. So it was asked to find out the response of vibration for damped case, and we have the equation for damped case: e raised to minus nt x0 cos root p square minus n square t plus n x0 plus x dot 0 by root p square minus n square sine root p square minus n square into p. Okay, so we have n by p is equal to 0.5, so I can write n is equal to 0.15 into p. Substituting this value in the equation omega is equal to root p square minus n square, then the omega is 12 p square minus n is 0.15 p whole square. Okay, so solving this equation, you will get the value of p as 12.137 and n as 1.82. Now substituting these values, n is 1.82, p 12.137, and t was given the value of t, time is equal to 0.12 second. Substituting these values, x0 was 0.5 meter and x dot 0 as 0.1 meter per second. Substituting all the values in this equation, then you will get the value of x as 0.43. So this is the solution for this problem.